All right, so what we're going to look at now is numerical integration. We've already done one form of numerical integration when we were doing Riemann sums. So all of this integration is to approximate area. We are doing approximate integration. We are not doing exact. So the question comes up, why not just do exact? Sometimes you can't actually integrate the function. Sometimes you don't have a function that would allow you to integrate. And then the best option you have is an approximation. So we're looking at approximation. So if I have a function, let's call it here f of x over an interval from a to b, we looked at left hand and right hand Riemann sums. But that's not the only way you can use Riemann type sums to calculate or approximate the area. So if I break this into however many subintervals, then what I see here is I have a delta x. Oh, I gotta get the ruler out of there. I have a delta x, and I have, if I did the left endpoint, I would make a rectangle. So we did for Riemann sums, and use that to approximate the area of that rectangle. So I could do left-hand Riemann sums. I could do right-hand Riemann sums. But what we're going to look at today is a few other kinds. So here, if I did a right Riemann sum or right hand endpoint for that, I'm seeing that neither of these are good. Some are better. And with this graph going up and then coming back down, I'm going to have an overestimate or an underestimate. And sometimes the rectangle's below and sometimes it's above. So this idea that right hand Riemann sum or left hand Riemann sum are my only options does not seem like the best idea. So what if instead of looking at the left hand like I did in the blue or the right hand Riemann sum like I did for the orange, what if let's look at green here. We still have the change in x. I'm still talking the same sized interval. But now what I'm going to do is, what if I go from the midpoint and go up to the curve, and then I make my rectangle from there. That's going to be the height of my rectangle. And now I see on the left hand side, I'm slightly below, but then it goes slightly above on the right hand side here. It won't always do that, but it does nicely for this one. And it feels like a closer approximation perhaps than a left hand or a right hand Riemann sum. So when we looked at Riemann sums, we looked at this summation notation from 1 to n, as I goes from 1 to n. That just means my first subinterval, my second subinterval, my third subinterval, all the way up to the nth subinterval. Before we looked at the left hand x value, f of the left hand of the interval or the right hand of the interval, and that would be an approximation because this gave me the height and this gave me the width. So I was making an area calculation. But what this x sub I asterisk is actually saying, I'm not saying left hand or right hand. I could actually, from any x value inside that interval, create a rectangle and add up all of those rectangular areas and get an approximation for that integral as well. So before we just looked at left hand and right hand, But now we have some more options. So the first one we're going to look at is the midpoint rule. So if I were to look at this, let's go from 0 to 6. And let's break it into intervals of 1 unit. So we'll go over that interval. So now I'm going to go 1, 2, 3, 4, 5, 6. Let's go 6. I'll count by ones. Duh, that makes sense. So my delta x is going to be my interval from 0 to 6. And let's divide it into 6 subgroups. So my delta x is going to be 1. So for my midpoint here, between 0 and 1, at 1/2, I'm going to go up to the function, and that's going to be the height. The function value at the 1/2 is going to be the height of my rectangle. And then I have the width is still my delta x. It's still 1. So there is my rectangle I'm going to be adding. And I can do that for, let me mark off my subintervals here, 2, 3, 4, about 4, 5, and then 6. And so if I do my midpoint for all of these, I'm going up to the function value and making rectangles. And what we should be seeing for most of these is I'm seeing a little above, a little below, and it's going to be a better estimate than my left Riemann sum or right hand Riemann sum. So here I have my rectangle. Oh, this ruler is going to drive me crazy. So from the point where the midpoint reaches it, we should see that each of these is in that interval. We've got some above and some below. So my rectangle looks something like that. So my midpoint rule then is going to be that the integral from a to b, if I look at what's happening there, of f of x dx is going to be approximated by each of these. The width is delta x. And now the height is at the midpoint. So I'm going to take delta x. I could write it with each function or with each rectangle, but it's going to be the same in all of them. So I can factor that out. And then now I'm going to take the function value at the midpoint. So x1, x sub 1 is my first the x value on my first interval plus f of x sub 2 for my second interval, all the way up to f of x sub n. Now this is just an x value. How do I designate that I want the midpoint? Well, the midpoint is an average of the two endpoints. So the change in notation here is we're going to have x bar. That this means the average. So I have the first x bar 1 is my first average, or the average over the first interval. So I'm going to take x sub 1 minus x sub 0 and divide it by 2. That's how I get my midpoint. So all of these are going to be averages, the x bar. So if I wanted to approximate the integral from 2 to 4 of this function x squared plus 2x dx, I am going to need to know how many intervals. We're going to do 4 equal subintervals. So that means that my delta x is going to be the width of the interval, 4 minus 2, over the number of subintervals. So I'm going to have a delta x of 1/2. So my midpoint, if I'm using the midpoint formula, or the midpoint rule, what I'm going to do is look at, several of you like to do it this way. If I'm going from 2 to 4, and I'm going to divide it into 4 subintervals, 3.5. Then what I'm going to do, like we did when we did the Riemann sums, is go in and put in those numbers. So halfway between 2 and 2.5 is 2.25. Halfway between 2.5 and 3 is 2.75. Halfway here, 3.25. And halfway here, 3.75. Oftentimes making the chart like that helps make sure we get the right ones. So what we're going to now do is multiply delta x times f of, we have 4 intervals. So I have 4 function values, 4 heights. The width is delta x. And what I'm taking these of is my midpoints, or the average over that interval, the average x value over that interval. So when I plug this in, I have delta x was 1/2, and I now have f of 2.25. Oops, I should do that in red. I'll put this in red so I see where it's coming from. So I have f of 2.25, f of 2.75, f of 3.25, and f of 3.75. So when I plug this in, I'm going to have 1/2. Oops, this should be in purple. I'm going to have 1/2 of 2.25 quantity squared plus 2 times 2.25. And then 2.75 quantity squared, et cetera, et cetera. And 3.75 squared plus 2 times 3.75. So I have that whole calculation. At this point, if you were on the AP exam, you could leave it like this. More likely than not, this would be on the calculator active part of the test. And so you could then just plug this into the calculator, which I'm going to do. And I got about 30.625. Now, the cool thing is, if I were to integrate that, so if I go math, I don't need that. I can do option 9, and we're going from 2 to 4 of, the function was x squared plus 2x dx. If I integrate that, I get, looks like 30 and 2/3. So what it actually equals when I integrate it looks pretty close to what our approximation was. So that midpoint approximation was not a bad approximation for that. The next rule that we're going to look at, because midpoint is one way that you can calculate numerical integration, or a approximate integration. The other way you can do this is using the trapezoidal rule. So if I were looking here, let's say we go from 1 to 4. So at each of these endpoints, I'm going up to the function value. Left-hand Riemann sum is going to put a lot above or below. Right-hand Riemann sum is going to put a lot above or below. We have our delta x here. Even midpoint is going to have some above or below. What if instead of using rectangles, we used trapezoids to approximate the area? So if I'm looking at this, I can see that a trapezoid actually is following along the curve relatively closely. That seems like I'm not having as much above or below error here. So if I were to do, this is f of x, the area of a trapezoid, if you remember, if you don't, I'm going to tell you. The area of a trapezoid, we have the height of the trapezoid, and then a trapezoid has two bases, base 1 and base 2. The area is calculated by taking half of the height times the sum of the bases. So if I envision my trapezoid vertically, that means the height of my trapezoid is my delta x. And then my B1 and my B2 are the function values at the end of the subinterval. So if I were to approximate, if I were to take the integral from 1 to 4 of this function f of x dx, and I were going to approximate it, I'm using the trapezoidal formula. For this trapezoid, I'm going to take 1/2 my delta x times the height, which is, half is for the formula. My delta x is the height, which is 1. And then I'm going to multiply by f of 1 is base 1 and f of 2 is base 2. And then if I were to do the second trapezoid, so that one, I will add to it. Again, I have half from my area of a trapezoid times my delta x. Now I have the left base, in this case base 1 is now f of 2, and the other end is f of 3. And then lastly, if I do this trapezoid, I now have 1/2 times 1 times f of 3 plus f of 4. And what I'm noticing is that, hopefully I'm noticing, 1/2 times 1 comes out front, and my sum is going to be f1, I'll do these in green, f1 plus f2 plus f2 plus f3 plus f3 plus f4. And what it looks like is happening is my inner end values are in parts of two different trapezoids, and then my end of the interval only occur once. So what I see is 1/2 times 1, and I get f1 plus 2 times f2 plus 2 times f3 plus f4. So if I generalize that, these are my end values, the end of the interval. So what I have here, if I am approximating from A to B of f of x dx, I am going to have 1/2. The 1 was my delta x. And then inside, I'm going to have f of a, the left endpoint, and then 2 times f of whatever this is going to, well, let's go, this is my left endpoint. Instead of a, let's call it x sub 0, and then 2 of x sub 1, and then 2 times f of x sub 2, all the way up to 2 times f of x sub n minus 1, and then f of x sub n. And x sub 0, this is how I want to do it. X sub 0 was your a value, and x sub n was the b value, the end of your interval. So if I wanted to use a trapezoidal sum to approximate this integral, I need to know if I need, let's do 4 subintervals again. So my delta x is going to be the width of my interval divided by my subintervals. So I'm going to get a delta x of 1/4. And then I like drawing this diagram so that I can see what my x sub 0, x sub 1, x sub 2 are. So I'm going from 2 to 3. And then this one is 2.25, 2.5, 2.75. So when I use my trapezoidal rule, I'm going to take the formula for the area of a trapezoid, 1/2 the height, and the height is my delta x, times I want f of 2, and then I want 2 times f of 2.25 plus 2 times f of 2.5 plus 2 times f of 2.75, and then f of 3 only occurs once because the end values are only involved in one trapezoidal calculation. So when I plug these in, 1/2 times 1/4 times 2 over 2 squared plus 2 times 2 over 2.25 squared plus 2 over 2.5 squared, 2 times 2 over 2.75 squared, and then I have 1, which is 2 over 3 squared. And again, at this point, I could type this into the calculator on the AP exam. If you did not have to calculate further, you could stop there. I'm going to type this all into my calculator and get approximately 0.3352. If I were to put this in my calculator and calculate this integral exactly, I get 1/3, which is, again, a relatively 3.3352 is a relatively good approximation. Now, this is using these rules, but most of the time, the argument, why would I need to approximate it when I can integrate it, is a good argument. And most of the time on the AP exam, you are not going to be asked to use these rules when you are given a function that we can integrate. The way you are going to see this is from tables. Okay, so I have some function, but I don't know what the function is. So in the real world, where you would see this is oftentimes we are conducting an experiment and I just have data values. I don't know exactly the function that's being represented. So they oftentimes are also not equal intervals. When we were using the rules with the functions, we had a fixed delta x, fixed delta x right here. We calculated it here. Where did I calculate it? Oh, we just looked at it from the graph. We had a fixed delta x. But here, if you notice, 2 to 6 is not the same gap as from 6 to 7 or from 7 to 10. Here are the function values that go along with these ordered pairs. So what I would like to do, we are going to approximate using this from this table, a left-hand Riemann sum and a right-hand Riemann sum. I should move the table down so we can see it. So the same idea, my left-hand Riemann sum. So if I am approximating from 2 to 10 of f of x dx, I am going to I need the area, which is base times height. So for a left-hand Riemann sum, these are my left-hand x values and corresponding y values. So my delta x for my first interval is 6 minus 2. And then I'm going to multiply by the function value of the left-hand endpoint. And then, so that's this one. Let's go here. On this interval, now my delta x is 7 minus 6. Could I do that subtraction in my head? Absolutely. And then I'm multiplying by the function value at my left endpoint. And then the last interval, I'm going to have my width is 10 minus 7, the length of that interval, times f of my left endpoint. So when I do this calculation, I have 4 times f of 2 was 5. And then here, 7 minus 6 is 1, and f of 6 is 15. And then this calculation, 10 minus 7 is 3. F of 7 is 17, which gets me approximately 86. For the right-hand endpoint, Riemann sum, same notation, 2 to 10 of f of x dx. I am going to now do my same interval, my same delta x, but now I'm multiplying by f of 6 because I want the right hand. Those are now going to be the 15, 17, and 11, 6, 7, and 10. And then I will have, again, plus 7 minus 6, but then I'm going to multiply by f of 7. And the last interval, still 10 minus 7, but now I'm multiplying by f of